Welcome to The Explainer. Today we're unpacking what I can only describe as a massive paradigm shift in AI agentic reasoning. We're looking at a state-of-the-art paper that takes large language models away from this clumsy, step-by-step stumbling and introduces a fundamentally new approach: fluid, continuous reasoning. The framework is called FlowAgent, and it's honestly going to completely change how we think about multi-tool orchestration. So let's just dive right in.
To start, we really need to hook into our core problem. Why do these incredibly smart AI models just suddenly break when you give them a long multi-step task? Think about a query like, is flying from Chicago to LA cheaper than flying to San Francisco? An AI has to search a database, calculate costs, and compare values. But all too often, halfway through this chain, it just hallucinates a tool or passes the totally wrong argument, and the whole operation crashes. So why exactly does that happen?
Well, to answer that, we're going to take a structured journey through the source material today. First, we'll examine the step-by-step trap. Then, we'll enter the FlowAgent framework itself. From there, we'll map the latent space, unpack the closed-loop advantage, and finally, look at the actual empirical results that prove its superiority. All right, part one, the step-by-step trap. This right here is the fundamental flaw in how current baseline LLMs handle planning. There is a stark contrast between local, myopic tool selection and severe error accumulation. You see, current LLMs select tools blindly, basically one by one. They formulate tool planning as an autoregressive generation task over a discrete space, meaning they look at the current context, pick a tool, and just move on. The problem with that? It completely lacks a holistic global perspective. Because they treat each step in total isolation, a single suboptimal choice, like calling the wrong search ID, completely derails the entire subsequent reasoning chain. The researchers put it pretty bluntly, stating, a myopic execution strategy becomes fragile, causing execution failures to compound rapidly. When you treat a long-horizon task as just mere token-by-token generation, you have absolutely no macro-level view of the mission. One mistake at step 2, and literally steps 3, 4, and 5 are just doomed.
Which brings us to part 2. Enter the FlowAgent.
This represents a huge paradigm shift away from explicit, discrete tool labels. Let's see how this builds a totally new framework. Taking the user input and the current context state, the system doesn't just jump straight into picking a discrete tool. Instead, it moves into what's called a conditional flow planner. Here, the system actually maps out a macro-level continuous trajectory in a latent space before it ever commits to a specific discrete action. It provides a global planning perspective to ensure the execution actually stays coherent.
Think of it like this. The traditional stepwise method is basically like a driver navigating a really complex city in super thick fog, only looking about 5 feet ahead of their bumper. They might make a locally optimal turn that ends up trapping them in a dead end. FlowAgent, on the other hand, is like a driver using a GPS satellite to map the continuous trajectory of the entire route from above before ever pressing the gas pedal.
Okay, moving on to part 3, mapping the latent space.
So how exactly is it calculating this global plan? Well, FlowAgent reconceptualizes discrete tool chaining as a continuous evolutionary path within a semantic space. Instead of relying on rigid, hard-coded tool labels, it translates the heavy math of ordinary differential equations and conditional velocity fields into a highly visual, fluid map of semantic concepts. The AI is literally evolving its reasoning plan across a mathematical space.
And because we're operating in this semantic space, we get a huge bonus: grouping by functional similarity. Tools are parameterized by continuous semantic embeddings. This means the FlowAgent actually understands what a tool does, its functional description, rather than just memorizing an isolated text label. By bypassing those isolated categories, the system can smoothly adapt to novel tool sets it has literally never seen before, all because it recognizes their functional neighborhood in the latent space.
Next up, part 4, the closed-loop advantage.
Generating a great global plan is honestly only half the battle, right? Because real-world environments change the second you interact with them. To strictly attenuate error accumulation, the agent interacts dynamically using a 4-step closed-loop execution scheme. It generates the global latent plan, sure, but it only executes the first step. Then it actively absorbs real-world environmental feedback, like a database actually returning a specific query result. Finally, it deterministically updates the context state and replans the rest of the trajectory. The researchers formalize this as a receding horizon generator. By dynamically resampling the latent plan based on updated states, it fundamentally suppresses cascading errors.
You aren't just blindly following an outdated plan if step 1 slightly changed the environment. And this closed-loop execution is mathematically proven in the paper to strictly attenuate long-horizon error accumulation.
Finally, Part 5, the final results.
All this fancy math sounds amazing, but how does it actually perform in practice? Well, I want to start with this number right here, 12.29 minutes. That is a massive computational efficiency gain. FlowAgent trains in just 12.29 minutes, whereas the reinforcement learning baseline, tool RL, requires a sluggish 48.75 minutes just to reach optimization. This massive efficiency boost happens because FlowAgent entirely skips the huge simulation overhead required by discrete policy optimization. Tool RL eats up over 68 gigabytes of average peak memory across 3 GPUs, compared to FlowAgent's 55 gigs. By using direct regression on the latent trajectory via continuous flow matching, it saves time, it saves memory, and it performs significantly better.
And when you look at convergence speed, specifically on the retail success metric, which is the absolute toughest database-backed domain in their benchmark, the results are striking. FlowAgent rapidly converges within just 4 minutes and stabilizes at a significantly higher success rate. ToolRL, on the other hand, drags on past 8 minutes and still levels off with a much lower final performance.
But honestly, this might be the most stunning result of the whole paper: generalization performance on strictly unseen tools. FlowAgent maintains up to a 78% accuracy on the Quen architecture when tested on tools it was never even trained on. The baselines experience a massive performance drop, hovering around 55 to 60%. Because FlowAgent actually learns the continuous semantic layout of tool functions, it has an unprecedented ability to adapt to novel schemas on the fly.
We've seen how shifting from myopic, step-by-step guessing to continuous, plan-level reasoning completely transforms an AI's ability to navigate complex tasks, correct its own errors, and adapt to totally unseen tools. Which leaves us with this final thought. If AI agents can now seamlessly map global trajectories and dynamically adapt their reasoning in real time, what limits are actually left on autonomous workflows? FlowAgent really proves that the next era of AI won't be about teaching models to take the right step, but teaching them how to flow toward the right destination. Thanks for joining me on this explainer, and I'll catch you on the next one.